Hi everyone, welcome to the Convert channel. In this session, we want to learn how to separate benzene, toluene, and xylene. As you can see within this figure, this is known as a Petlyuk distillation or Petlyuk configuration, which is highly usable in many industrial and petrochemical companies. And you will also learn how to run a recycle block, as you can see within this figure, which if part of its stream is going recycle back to the first column, which is the pre-fractionator. And I want to teach you how to I want to teach you a simple trick how to run a recycle block without any convergence or whatever you may have encountered it. And you additionally learn how to add a new spec within the software and you run the main column, which is highly recommended. As my experience, I use those two spec, which is the reflux ratio and the boil up ratio. But for easier access, uh, I have provided all the information. I want to use benzene, toluene, and xylene, which is vapor fraction of each component are provided in this table, and we want to use NRTL property package because finding those information within this article is quite challenging. I have provided all the information within this previously simulated file. And I highly recommend you to stop the tutorial and add the information within this figure and check it out with me if you have any to check it out where you went wrong with your self. So let's start the simulation. As you can see, we have a fit which is given within this figure. To save time, I have previously define this fit. And for the recycle one stream, as you can see, the molar flow rate is 50 and its temperature should be logical since the it is closer to the condenser stages. Its temperature should be lower than the recycle 2 stream. So it is recycle 1 stream gives 140, and for the recycle 2 stream, which is closer to the reboiler, which should be around, for example, 160 degrees C. And the composition of each of these two streams are provided. So you can see it for the recycle 1, we have 50% of toluene and xylene. There's no benzene content. We have a simulation since it is not close to the like component, which is this case is the benzene, and we have 90% and 10% of the xylene and toluene respectively for recycle 2 streams. So let me jump into the simulation and learn how to run our simulation properly. So add the a column within the simulation environment and change this into 34 stages and design the feed stream for our feed, and it's entered into the column at the stage 7. In the top stage inlet is recycle 1 and the bottom is recycle 2, and the overhead width is V1 and bottom stage is L1. So click on next, and the top stage pressure is 190 kBA, and since the column is working at a constant pressure, the working pressure should be same as the top stage pressure. So if you have any information about the temperature estimation or whatever you have in this actually with your simulation or whatever you have, you could guess, you can adjust the value, but my recommendation is just to skip this page as well. So once you complete, you can easily click on run and check it out if it is going to run properly or not. So as you can see, it would not run simply because that's heat spec tolerance is on the order of 10 power by -1, which is not less than this predefined value of within the HYSYS. So my recommendation is that to switch the solver or solving method from this drop-down menu to the modified solver. Once you do that, you can easily click on run, and we converge the first column properly because we have two components, which is their boiling temperature are quite closer to one another. It's highly recommended to use the modified HYSYS salt. So at the second column within the simulation environment, and define those stream for this column. Just adjust the number of tray into 60 according to the article, and the energy of condensor is QC and condensor is total, and this stream is benzene, which is the light key, and the middle stream is toluene, which is the middle key, and the bottom stage should be xylene or the heavy key at this stage, and the feed stage should be V1 and L1. V1 enters the column at the stage at 15, and L1 internal stage is 45. So once you define all those information, you have forget about the boiler energy, just name it as well, and then click on the next. Just skip this page. Condenser pressure is 190 kPa, and the boiler pressure is the same as the top stage. Click on next. We do not have any temperature estimation, and I want to skip this page because I want to teach you a simple trick how to run your simulation without actually adjusting those value within this window. So once you add define all those information, you can click on the monitor tab, which is the specification tab of your column. You can adjust this value or activate or deactivate the specification or whatever you need, and adjust this value to run your simulation. As you can see, degree of freedom is 0, and we have 3 activated spec, and we should adjust those value, and distillate rate. So we should approach it logically and adjust this logically. If we get back to the previously simulated file, we have benzene, which is the distillate one, and its vapor fraction is 0.4, and the total molar flow rate is 100 kg per hour, and by multiplication of those two values, we have 40 actually kg mole per hour for the distillate rate. So I wanna adjust it into 40, which is the distillate rate, and for the reflux ratio, let's start with 20. And I highly recommend you to run your simulation with the boil up ratio, which is quite easier to run your converge and converge your channel your distillation column with the reflux ratio and the boil up ratio than other specifications. So for the boil up ratio, let me start initially with for example with 60. So deactivate this spec and activate the boil up ratio or a new added spec within this figure. So benzene, toluene, and xylene are separated. But you might be wondering why I didn't added this V1 return and L1 return as within this figure, within this file. But my recommendation is that to run your simulation without those recycle the same. Then once you convert your column, you can get back to the actually connection tab of the distillation column and add those stream. Define those stream, and this stream is V1 return, and another stream is L1 written. I highly recommend you to run your simulation without adding this stream to your simulation to have a better convergence initial. So T, which is the toluene, is going to leave the distillation column at stage 30, and the V1 withdrawal stage is a stage 40, and for L1 withdrawal stage, let me just adjust it into 47. So once you define those withdrawal stages, you should get back to the spec monitor and adjust those to a new added spec within this flow video. So it'll be initially a start beat 50, but you might be wondering again why I do is adjust it into 50, because as you can see, recycle 1 stream total mole flow rate is 50, and recycle 2 molar fluid flow rate is 50 kg mole per hour, which this is a sign to or an indication to start your simulation with the same value as you have defined previously with recycle 1 and recycle 2 respectively. So once you define all those specification, degree of freedom is 0, and we have 5 activated spec, then you can run your simulation. So once you add it, converge your distillation column, you can in this part I wanna teach you how to avoid convergence error with recycled block. My simple trick is that so let me just connect this to value and I want to talk about. Just press Control, and you can, once this blue square appear, you can connect this to the recycle 1 and do the same for the recycle 2. And my simple trick is that to just click on the boom tab and make sure that the solver of the HYSYS is switched on hold, which is highly recommended once you wanna connect the update of recycle plug within the software. So once you switch the solver into on hold, you can connect this stream to the recycle 1 and 2. So you can again switch it back to its normal condition, but as you can, the heat spec is not quite well, so you can get back to the solver is perfectly defined, and we do that with total number of stage is correct. So let me change the temperature of 90% toluene, and we have 133. Let me just adjust it to 120, 130. And then for recycle 2, it should be 116, which it should be higher than the recycle 1 stream. So once you define this first column, you can go to the second column, and its tolerance is not quite well. We should stop the solver and then go to the parameter tab. Under this parameter tab on the left side toolbar menu, you can switch this into the modified HYSYS solver. So let me check it out. What is our spec? It's 20 reflux ratio, and we have distillate rate, and recycle 1 and 2 are defined. Let me increase this value into 60, for example. So then again, run your simulation. So as you can see, we have converged these two columns without any convergence error within the recycle block. So in this part, I want to add a spreadsheet within the simulation environment to teach you something new about this. How to, I wanna, for example, uh, change the reflux ratio and the boil-up ratio within the spreadsheet, and while continuously monitoring the design spec or mole fraction of the B1 stream. So let me just click on the B1 stream, right click on the B1 stream, then on the table, remove this predefined variable and look for the master component mole fraction of the benzene, which is the light component. You can add or this spec and this within the for the toluene and the xylene stream, but so for actually saving our time, I just simply provide these tables just for the benzene. So you can go to the column environment, and under the monitor tab, you can copy reflux and the boil-up ratio, which is highly recommended to run your simulation with these two specs, which is quite easier to run your simulation with other than actually that other specifications. So this one is the reflux ratio and this one is the boil-up ratio. You can easily adjust these two value while continuously check your applet specification, which in this case is the mole fraction of the benzene, and check it out if it is pretty match with your desired specification or not. So I want to change it where the boil-up ratio, for example, E270. You can continuously change if it's pretty matched with your desired specification or not. As you can see, you can change this to a spec as well. You can do the same procedure for the toluene and the xylene and check it out if your molar composition of these two stream is match with your desired specification or not. I hope you found this tutorial helpful. Then if you haven't found it helpful, I highly recommend to not subscribe my channel. However, I hope you found it helpful. Have a good time. Bye bye.